So in CRC, an m-bit message is represented by this polynomial. We already saw this before. The sender and receiver agree on what is called a divisor polynomial. Now this divisor polynomial has a degree k, which is equal to the number of redundant bits that you are going to add. For example, this is an example of a divisor polynomial. So this has degree 3. That means if you are using this divisor polynomial, you are going to add 3 redundant bits. So the choice of this divisor polynomial is what determines your error detection capabilities, and this is derived very carefully based on the observed error patterns. So for example, in Ethernet, this is the CRC polynomial that is used, which is of 32 bits. So you add 32 redundant bits. In HDLC and DDCMP, you use 16 bits. So pay close attention. This is the crux of CRC. The sender sends m message bits and k redundant bits. So this is the transmitted message. I'm going to represent this by this polynomial px. So the idea here is to derive px from the message such that this is exactly divisible by cx. So when you receive a message Rx, if there are no errors, the Rx will be exactly equal to Px, in which case it is exactly divisible by Cx. But if there are errors, this Rx will not be equal to Px, and then very likely it will not be divisible by Cx. Notice the use of likely again. So it's possible that certain error patterns may result in an Rx which is exactly divisible by Cx. But as I said, your goal is to design Cx such that most common errors can easily be detected. So how do you make this Px exactly divisible by Cx? So you know mx, which is the message, you know Cx, this is given. Now your goal is to generate the transmitted bits based on the polynomial here. So the first thing you do is you multiply this message by x to the power of k. So basically you are doing this results in adding k zeros at the end of the message. So you get a temporary polynomial, let me call it tx. And now what you do is you divide the tx by cx to get a remainder. And now just subtract this remainder Rx from the Tx and then you get this Px. Now this Px is exactly divisible by Cx because you are subtracting the remainder from the Tx. So here is an example that gives you an idea of what is happening. 37 can be expressed as 7 into 5, 35 plus 2. Now this 37 is like this T. And let's say 5 is like this C. Now what you're doing is you're dividing T by C and you got this remainder R. Now you're subtracting this R from the remainder, so that P is going to be 37 minus 2, that is equal to 35. Now this 35 is exactly divisible by C, which is 5. So the same thing is shown here. So the Tx is x to the power of k multiplied with mx. This is qx cx plus rx because this is polynomial division. This is how I'm expressing it. Now px is from tx you are subtracting rx, so this is what it boils down to. And remember, arithmetic additions or subtractions are the same when you do modulo 2. So this turns out to be this, which in turn is equal to qx cx, which is makes px exactly divisible by cx. So the coefficients of this remainder polynomial are basically the redundant bits which you add to the message bits and transmit. So here is an example that should make things very clear. So this is the message, the bits that I wish to transmit. So I'm representing it with the message polynomial. And here is the divisor polynomial. This turns out to be x cube plus x square plus 1. Note that the degree is 3, which means k is equal to 3. So the temporary bits are obtained by adding the 3 redundant bits, basically zeros at this stage, to the message. So this is the temporary thing. The temporary polynomial is obtained by multiplying the message polynomial by x to the power of 3. So that becomes 10, x to the power of 10 plus x to the power of 9 plus x to the power of 6 plus x to the power of 4 plus x to the power of 3. Now I'm going to divide this temporary polynomial by the divisor polynomial. So this is what it boils down to. So x to the power of 7, it is x10 plus 9 plus x to the power of 7. So these terms kind of cancel out. We have x7 plus x6 plus x4 plus x3. Again, I'm going to do this. It is x7 plus x6 plus x4. In fact, all these terms are kind of cancelling out. Now you have x3, so I have to do one more. So this is x3 plus x square plus 1, which leaves me with x square plus 1. So this is the remainder. So the remainder, as you can see, translates into these bits. Now I'm going to add this remainder to t, basically substitute these last 3 zeros with the remainder. So this is going to be my transmitted bits. So by the way, this division was done using modulo 2 arithmetic. So addition subtraction turned out to be the same. So here is the error detection capability of CRC. So if there were error, basically what you receive will be the transmitted polynomial and the error polynomial, where this error polynomial captures the bitmap of the position of errors. So basically if you add this, that means in those positions where there is a 1 in E are the places where the bits got flipped in the transmitted bits. Now we know that Px is exactly divisible by Cx. That means you cannot detect errors if Ex is also exactly divisible by Cx. So the goal is to design Cx such that for anticipated error patterns, Ex is not divisible by Cx. So how do we do that? Let me work out an example again. Suppose we want to design a divisor polynomial such that it can detect all instances of odd number of bit errors. Given that the error polynomial shows the bit positions where the errors occurred, and given that we want to capture odd number of bit errors, what do you think is the characteristic of the error polynomial? So that's right, this error polynomial will contain odd number of terms with coefficient of 1. Basically, wherever the bit error has occurred, you're going to have the term with the coefficient of 1, and since you have odd number of bit errors, you'll have odd number of terms. Now if I were to substitute x is equal to 1 in the error polynomial, naturally since it has odd number of terms, e of 1 is going to be equal to 1. Remember, I cannot detect errors if Ex were exactly divisible by Cx. So given E1 is always going to be equal to 1 for odd number of bit errors, what should C1 be equal to if Ex is exactly divisible by Cx? So let me write this as Ex is Cx times some other polynomial Ox. In this case, Ex is exactly divisible by Cx. So if I were to substitute x is equal to 1 here, this one is equal to 1. So what should this be? So that's right, C1 has to be equal to 1. If it were equal to 0, E of 1 is also going to be 0, and we don't want that. So remember our original goal, we don't want Cx to be a factor of Ex. So if Cx were a factor, it needs to C1 to be equal to 1. So in this case, we need to set C1 is equal to 0 if we don't want Cx to be a factor of Ex. So now how do you design a divisor polynomial such that when you substitute x is equal to 1, it is going to take on the value 0? Basically, if it has a factor of the form x to the power of I plus 1, then C1 is bound to be equal to 0. So there you go, we devised a divisor polynomial that can detect all instances of odd number of bit errors. If I were to set Cx is equal to x plus 1, we have seen this algorithm, error detection algorithm before. Which one is it? That's right, even bit parity. So remember, this has degree 1, so there also we introduced 1 bit of redundancy. Just like how we have designed a divisor polynomial for capturing odd bit errors, you can devise similar such polynomials. For example, if you want to capture all single bit errors, this divisor polynomial should have x to the power of k and x0 to be non-zero coefficients. And similarly, if you want to catch all double bit errors, Cx should have at least 3 terms. This we already saw, where all odd bit errors can be captured if Cx contains the factor x plus 1. And similarly, any burst of length less than or equal to k can be captured if Cx includes the constant term. So these are not difficult to prove. I will leave it up to you to work it out. Another point that I need to emphasize is that CRC algorithm as such is very easy to implement on shift registers. That is why it's very popular. So here is a summary of what we have seen in this video. So it's important to detect errors, and there are many techniques for error detection ranging from the simple parity to all the more complex CRC. So going forward, we will see how to recover once we detect an error.